Hey, so this is a strain gauge. Not really. This is kind of what it looks like physically. So really, in reality, these are about the size of a fingernail. I've just blown it up here to show. So the idea behind a strain gauge is basically that you have a wire, and when you stretch a wire, the resistance of that wire changes just a little bit. It's very, very small. So this, from a circuit diagram standpoint, really looks like just a resistor. And commercial strain gauges typically look like this. So it's basically just a really long wire that's run back and forth many times. And it's usually made out of a thin metal foil. And the idea is that you can glue or epoxy this thin metal foil, little strain gauge, onto a piece of metal or something that will flex just a little bit when force is applied to it.
This is a picture of a strain gauge sensor that's inside of a small digital scale that I own. So I took it apart. You can see right here is the strain gauge sensor itself. It's under some, I guess that's white epoxy. But underneath there is, I'm sure, one of those little foil sensors. And this point here is where the sensor is mounted to the base of the scale. And this other point over here is basically where the weight is concentrated for the scale. So basically it's going to take this metal bar and basically turn it into kind of a lever.
So this type of sensor is used very commonly in any kind of electronic scale. So for weighing anything from a piece of mail all the way up to, trucks. And it can also be used for things that you might not think of, like you could actually put sensors like this onto the structure of a bridge, for instance, and you could measure the forces that are on a bridge. You could probably even measure cars going by how much that moves the structure of the bridge. You can also do things like mount these on the wings of airplanes and then test what stresses are being produced on the wing as air goes over the wing, things like that. So all sorts of kind of cool uses for this type of sensor. So the way this works, I mentioned already, is that the wire or the metal part of this sensor is stretched, and that changes the resistance. It's important to note that the stretching has to occur in a particular direction, and in this case, it's this way. And you can kind of see why. This is where most of the length of all this long wire is. So if you're going to stretch it, it's going to change the resistance the most by sort of changing all the resistances of all these little segments of the wire. If you change or if you put force on it in the other direction, well, you're really just changing, these short little wire segments here, which is not very useful. So you want to always apply force here. Okay, so I mentioned that strain gauges, the resistance change there is really, really small. Like if you hook up your multimeter to a strain gauge element and then flex it, you're probably not going to actually see a resistance change on the multimeter. It's because it's usually in the milliohm range that the resistance is changing. So there's some tricks that we can do to make this easier to measure. The biggest one is we often put strain gauge elements in what's called a Wheatstone bridge configuration. So this kind of shows this here. It sort of looks like a diamond or a square, whatever you want to say. And each side of that diamond is a resistor. And what we do is, I've labeled these E plus and E minus, S plus and S minus. So this stands for excitation voltage, positive and negative. So you could put some known voltage here. Whatever, 5 volts, 3 volts, 12 volts, whatever. And then E minus is usually either a negative voltage or ground. So that's just sort of powering the circuit, really. And then you measure from these two the other two corners of the diamond, which I've labeled S plus and S minus for sense plus, sense minus. So basically you'll read the voltage here. This is like a two voltage divider circuits together, really. So the reason we do this is because it doesn't really amplify the voltage, but it does make it it makes it easier to read by sort of isolating the resistance change. It's better than a standard voltage divider circuit, which you would kind of call a half bridge. So if you covered up this one side, that would be like a half bridge. There's a couple things to note here is these all look like regular resistors. You could have one active element, so meaning a variant, the strain gauge sensor here. So I've drawn a line through there. That usually means that's a variable resistor. So this is an active element, meaning it's a strain gauge sensor. These other ones could be fixed resistors. That's fine. You can have like two active elements, and even better than that, you can have 4. Now, a lot of strain gauges that you'll buy commercially will already be sort of configured in this, either a half bridge or a full bridge configuration, so you won't have to really worry about it too much. And I'm not going to get real deep into the wiring here because depending on the application, it can get complicated and it's a little tough to explain. But the important thing is to remember the Wheatstone bridge and sort of why we use it. So this is an old bathroom scale. Has 2 load cells in it, or 2 separate half bridges of a Wheatstone bridge. That's the 6 wires that are here, the red, black, and white. Okay, so here's the diagram of the circuit I'm using here. So I have it hooked up to an Arduino. I think it's over an I2C bus. And keep in mind, this is a functional diagram. This isn't an exact circuit diagram. The circuit diagram itself would be a little bit more complicated. There's various resistors and power supply circuitry and other things that are involved here, which I chose to leave out because I wanted to get sort of the high-level diagram. So basically, I've got my Arduino. It's communicating to an analog to digital converter, in this case a 16-bit one, through a serial bus. Doesn't really matter that it's I2C or SPI or whatever. That's an implementation detail. The important part here is this analog to digital converter will convert an analog voltage to a digital value that the Arduino can use. Now there are onboard analog to digital converters on Arduinos, but they're 10-bit. They're not very accurate, and with this sort of application we want the utmost accuracy. Okay, so I upped it to a 16-bit. There are even 18-bit and 24-bit ADCs available. They get more and more expensive. I chose to play with the 16-bit because it was pretty affordable and gave me pretty good accuracy. This other part here is very important. This is an instrumentation amplifier. The point of an instrumentation amplifier is, as opposed to a normal op amp, it's optimized to have really accurate and clean outputs. So basically, it's perfect for this sort of application where we've got a Wheatstone bridge where the voltage changes here are going to be like in the millivolt ranges. They're going to be very, very small. And this instrumentation amplifier, which is more expensive than a typical op amp because it's so much more accurate, it's going to very, very accurately amplify that millivolt level signal to a small voltage like 0 to 5 volts or 0 to 3 volts. So it's important that you have a really high quality instrumentation amplifier. So if you search for instrumentation amplifier, you'll come up with a list of parts, and some of them can be quite pricey, but that's really what you want for this sort of job. Now, you'll see the circuit for this is kind of complicated. So this works well, but it is complicated, and a lot of these chips are pretty expensive. So there's the downside of this type of approach. Okay, so here's my new circuit. you probably saw the old one. It's pretty messy. 2 different breadboards, bunch more chips and resistors and things like that. Now I've got everything wired up to this little board, which has an HX711 on it. Okay, so here's my last diagram here. It looks pretty similar to the previous circuit diagram, but there's a key difference. One, all of this stuff, so the instrumentation amplifier and the analog to digital converter, and even the excitation voltages, so our VREF and our ground or E minus, excitation minus supply, notice, is inside of this green box. This green box is a functional diagram, at least that I drew. I'm not sure this matches the data sheet, but for a chip called an HX711. So this is basically a purpose-built chip that you can get for interfacing to strain gauge sensors. And it works really well. It's very inexpensive. And it has everything you need to measure a strain gauge sensor built into a single chip. It's also worth noting that this already has, you can interface it to an Arduino like we were doing before, or you can tie this directly to a Raspberry Pi. There are lots of different libraries available on the Raspberry Pi side and the Arduino side to interface to this specific HX711. This is probably one of the most commonly used chips for this purpose, and I've experimented with it a bit, and it works really well. So this is pretty much my answer now whenever I'm doing strain gauge sorts of applications, is I just use this HX711. Great chip, has everything built in. The circuit diagram is not very much different from this functional diagram because all the complex stuff is all integrated into that one HX711 chip. So you just pretty much connect your sensor to that and then connect a serial bus to your Arduino or Raspberry Pi or whatever. That's it. And it just works. Great little device.
Now, on the software side, there's lots of possibilities out there. There are really good Arduino libraries available, and there are also really good libraries available for the Raspberry Pi side in Python. So whatever device you're using, whatever interface you're using, there's probably already a software library written to interface to an HX711 out there. So thanks a lot for watching. I hope you learned something about strain gauges and load cells today. I may have future videos that kind of get into more like applications using these, but today I just wanted to talk through kind of the basics of how these work and what they do. Thanks for watching.